Hi, this is Tanet Lalilert. This is a final project presentation of CSAE E89 deep learning for 2025 Harvard Extension School. My name is Tanet Lalilert. Um, the title of my project is facial expression recognition. Um, Facial expression recognition has become increasingly important across field, but the traditional methods are limited. Because they rely on cell reporting, um, as a result, we need a better way to like to recognize the user expression. So in this project, my main focus is to develop a supervised deep learning model capable of classifying facial expression images into categories. So the data set is from for 2013 data set from Kaggle. There are seven categories: angry, disgust, fear, happy, sad, surprise, and neutral. The training set is about 28,000, and the test set is about 7,000. So these are like example images from angry, disgust, fear, happy, sad, surprise, and neutral. So the data exploration, the happy category contain most images, and the lowest number of images they are in the discuss category. Data pre- pre-processing. So I use data generators and data augmentation because it can prevent overfitting. So in data generator, image data generator, I use some augmentation like with chip, high chip, um, uh, horizontal flip, rescale, and then rescale so that is between 0 and 1. Um, and then in the uh, from directory, I convert to grayscale. So modeling, there are like five models in this study: CNN, efficient B0, efficient B0 with transfer learning, fine-tuning, ResNet 50, vision transformer, and Cosmix. The first model is CNN, convolutional neural network. Um, there are multiple components in CNN, like convolutional layer, activation layer, batch normalization, max pooling, fully connected layers. This is the CNN architecture. So this is how I build the CNN model, the code that I use. And this is the summary of the model. I have like a correlational layer, batch normalization, max pooling, and I trained the model for 50 epochs. So this is the plot of the model accuracy and loss. You can see that the validation and training accuracy graph, they increase like pretty smooth, and they converge, so the overfitting is not the issue here. This is confusion matrix. You can see like the happy has the most number. This is a observation, a summary of the training and validation loss and accuracy. Next is efficient net B0. Efficient net B0 is also CNN, but it has a compounding scaling, so it's a little bit it's higher performance. So this is architecture. This is how I build. The first one I built without the pre-trained model. Um, this is the summary. The trainable parameter is about like 4 million parameters, and I trained for 50 epochs. This is a graph of the accuracy and loss. You can see like the trend and validation accuracy increased throughout the 50 epochs. So it means the model is still running, and it's the graph converts. So we can see all fitting here, but it's a little bit unstable. Um, so because of the imbalance classes, and we see spike in the loss, so that's result from the imbalance classes. Observation summary. Next is we use the transfer learning. Transfer learning, we reuse the pre-trained model, so we don't have to. We can save some resources. This is how I build the transfer learning model. I use the way like ImageNet. And I train for 40 epochs. This is a graph. You can see that the validation accuracy does not improve, and the train accuracy improve at low rate. So we can this is because the pre-trained model is not helpful here, and um and the um and the model is underfitting. Next is fine tune. The fine tune, we unfreeze the trainable layer so we can train to our specific problem. So I unfreeze the last 20 layers. I train for 4 epochs. So similar to transfer learning model, the validation accuracy does not improve, and the training accuracy improve at low rate, so the model are underfitting. Next is ResNet 50. ResNet 50 is also a CNN architecture, but it use the ResNet connection to prevent the vanishing gradients. So this is the architecture of the ResNet 50, like convolutional layer, conversion blocks, residual block, fully connected layer. This is the visual like of the architecture. You can see the residual that we add at the end of the block. This is how I build the ResNet 50. This is the model summary. You can see that like the trainable parameter is about like 23 million parameters. Really high number. And this is a train for 50 epochs. This is a graph of the accuracy and loss. You can see that the accuracy like increasing throughout 50 epochs, but it's not really stable. The reason is because the regularization and the learning rate could be the issue for this. we have to like do some like hyperparameter for that. Summary. Next is vision transformer. Vision transformer is not CNN. Is the we use the cell attention mechanism for this model. Um, so this is the architecture. The key stages like image patching, embedding, positional encoding, transformer encoding, and classification here. For the transformer encoder, we have the multi-head attention to do the cell attention. Um, so this is the build how I build the vision transformer model. I have the helper function, multi-layer perceptron, and two classes for patches and patch encoder. Um, And in the build model, I have the multi-header attention for the cell attention. And this is a model summary. You can see like the trainable parameter is about 500,000. It's much lower than the ResNet 50, about like 23 million parameters. I trained for 50 epochs, and the plot, you can see the plot, the graph of the train and prediction accuracy. They're pretty smooth and converse, so we don't have the issue about for the overfitting. But the accuracy is below 0.5, so it's still like underfitting. Next is Kovnik. Kovnik is a CNN architecture, but it uses the design from the vision transformer. This is architecture. So this is how I build it. I use Kovnik Tiny and use a pre-trained net image. The trainable parameter about 200,000, and I trained for 10 epochs. And this is the graph. So you can see it's underfitting. And this is the 5 June. It's still also underfitting. So the conclusion. So surprisingly, CNN like perform best in all the 5 models. Um, the reason is because like the data set the image is really low resolution, like 48 by 48, because the most advanced models, they need like high resolution images, like 224 by 224. And another reason is the data set, they're really small. So for example, vision transformer require large data sets. So that's why CNN seem to be like performing best in this data set. And so the efficiency is a runner-up. We have some recommendation that CNN we can increase by adding some more block, and then we can improve the resolution for other models. This is reference. Okay, thanks for watching.